Hey everyone, how goes it, and welcome back to Computer Science 311. Today, we're moving on to main memory. The main purpose of a computer system is to execute programs. These programs, together with data that they access, must be at least partially in main memory during execution. Modern computer systems maintain several processes in memory during system execution. Many memory-managed schemes exist, reflecting various approaches, and the effectiveness of each algorithm varies with the situation. Selection of a main memory scheme for a system depends on many factors, especially on the system's hardware design. Most algorithms require some form of hardware support. In a previous lecture, we showed how the CPU can be shared by a set of processes. As a result of CPU scheduling, we can improve both the utilization of the CPU and the speed of the computer's response to its users. To realize this increase in performance, however, we must keep many processes in memory. That is, we must share memory. We're going to discuss various ways to manage memory. The memory management algorithms vary from primitive bare machine approach to a strategy that uses paging. Each approach has its own advantages and disadvantages. Selection of a memory management method for a specific system depends on many factors. As we have previously seen, memory is central to the operation of a modern computer system. Memory consists of a large array of bytes, each with its own address. A typical instruction execution cycle, for example, first fetches an instruction from memory. The instruction is then decoded and may cause operands to be fetched from memory. After the instruction has been executed on the operands, results may be stored back into memory. The memory unit sees only a stream of memory addresses. It doesn't know how they are generated or what they are for. Accordingly, we can ignore how a program generates a memory address. We are interested only in the sequence of memory addresses generated by the running program. We first begin our discussion by covering several issues that are pertinent to managing memory. Some of these are basic hardware, the binding of symbolic or virtual memory addresses to actual physical addresses, and the distinction between logical and physical addresses. Main memory and the registers built into each processing core are the only general-purpose storage that a CPU can directly address. There are machine instructions that take memory addresses as arguments, but none that take disk addresses. Therefore, any instruction in execution and any data being used by the instructions must be in one of these direct access storage devices. If the data are not in memory, they must be moved before the CPU can operate on them. Registers that are built into each CPU core are generally accessible within one cycle of the CPU clock. Some CPU cores can decode instructions and perform simple operations on the register contents at the rate of one more operation per clock tick. The same cannot be said of main memory, which is accessed via a transaction on the memory bus. Completing a memory access may take many cycles of the CPU clock. In such cases, the processor normally needs to stall, since it does not have the data required to complete the instruction that is executing. This situation is intolerable because of the frequency of memory access. The remedy is to add fast memory between the CPU and the main memory, typically on the CPU chip for fast access. This is commonly referred to as cache, as it has been described before. To manage a cache built into the CPU, the hardware automatically speeds up memory access without any operating system control. Not only are we concerned with the relative speed of accessing physical memory, but we also must ensure correct operation. For proper system operation, we must protect the operating system from access by user processes as well as protect user processes from one another. This protection must be provided by the hardware, because the operating system doesn't usually intervene between the CPU and its memory access. Hardware implements this production in several different ways, as we show throughout this lecture. Here we outline one possible implementation. We need to first make sure that each process has a separate memory space. Separate per process memory space protects the processes from each other and is fundamental to having multiple processes loaded in memory for concurrent execution. To separate memory spaces, we need the ability to determine the range of legal addresses that the process may access and to ensure that the process can access only these legal addresses. We can provide this protection by using two registers, usually a base and a limit, as you can see illustrated right here. The base register holds the smallest legal physical memory address. The limit register specifies the size of the range. For example, if the base register holds at 300,040 and the limit register is 100,900, then the program can legally access all addresses from 300,040 through 420,939 inclusively. Protection of memory space is accomplished by having the CPU hardware compare every address generated in user mode with the registers. Any attempt by a program executing in user mode to access operating system memory or other user memories results in a trap to the operating system. This attempt is treated as a fatal error. The scheme that prevents a user program from accidentally or deliberately modifying the code of a data structure of either the operating system or other users. The base and limit registers can be loaded only by the operating system, which uses a special privilege instruction. Since privilege instructions can be executed only in kernel mode, and since only the operating system executes in kernel mode, only the operating system can load the base and limit registers. This scheme allows the operating system to change the value of the registers, but prevents user programs from changing the register's contents. Usually, a program resides on a disk as a binary executable file. To run, the program must be brought into memory and placed within the context of a process. This is where it becomes eligible for execution on an available CPU. As the process executes, it accesses instructions and data from memory. Eventually, the process terminates, and the memory is reclaimed for use by other processes. Most systems allow a user process to reside in any part of the physical memory. Thus, although the address space of the computer may start at 0, the first address of the user process may not be at 0. In most cases, a user program goes through several steps, some of which may be optional, before execution. Addresses may be represented in different ways during these steps. Addresses in the source program are generally symbolic. A computer typically binds these symbolic addresses to relocatable addresses. Now, the linker or loader in turn binds the relocatable addresses to absolute addresses. Each binding is a mapping from one address space to another. Classically, the binding of instructions and data to memory addresses can be done at any step along the way. For instance, compile time. If you know at compile time where the process will reside in memory, then absolute code can be generated. For example, if you know that the user process will be residing starting at location, let's say R, then the generated compiler code will start at that location and extend from there. If at some later time the starting location changes, then it will be necessary to recompile this code. Another could be load time. If it is not known at compile time where the process will reside in memory, then the compiler must generate relocatable code. In this case, final binding is delayed until load time. If the starting address changes, we need only to reload the user code to incorporate the changed value. And finally, execution time. If the process can be moved during its execution from one memory segment to another, then binding must be delayed until runtime. Now, special hardware must be available for this scheme to work, as will be discussed a little later. Most operating systems use the execution time method. Here's a diagram of what was just discussed. As you can see, these are the different times where these addresses can be generated: compile, load, or execution. An address generated by the CPU is commonly referred to as a logical address. Now, this is different from an address that is seen by the memory unit. That is, it is loaded into the memory address register of the memory. Now, this is commonly referred to as a physical address. Binding addresses at either compile or load time generates identical logical and physical addresses. However, the execution time address binding scheme results in differing logical and physical addresses. In this case, we usually refer to the logical addresses as a virtual address. Keep in mind, we're going to interchange logic address and virtual address a lot. The set of logical addresses generated by a program is a logical address space. The set of all physical addresses corresponding to these logical addresses is a physical address space. Thus, in execution time address binding scheme, the logic and physical addresses differ. The runtime mapping from virtual to physical addresses is done by a hardware device called a memory management unit called the MMU. We can see that right here. We can choose from many different methods to accomplish this kind of mapping. Now, for the time being, we illustrate this mapping with a simple MMU scheme that is generalized of the base register scheme described previously. The base register is now going to be called a relocation register. The value in the relocation register is added to every address generated by the user process at the time the address is sent to memory. For example, if the base is set at 14,000, then an attempt made by the user to address location 0 is dynamically located to that location 14,000. Now also, if an address location is at 346, now that's going to be mapped to 14,346, as we can see here. The user program never accesses the real physical addresses. The program can create a pointer to location 346 stored in memory, manipulate it, and compare it with other addresses, all as simply the number 346. Only when it is used as a memory address is it relocated relative to the base register. The user program deals with logical addresses. The memory mapping hardware converts logical addresses into the physical addresses. Now, this is an example of execution time binding that we have previously discussed. The final location of referenced memory addresses is not determined until the reference is made. We now have two different types of addresses: logical addresses and physical addresses. The user program generates only logical addresses and thinks that the process runs in memory at location from 0 to max. However, these logical addresses must be mapped to physical addresses before they're ever used. In our discussion so far, it has been necessary for the entire program and all of the data of a process to be in physical memory for the process to execute. The size of a process has thus been limited to the size of the physical memory. To obtain better memory space utilization, we can use what's called dynamic loading. With dynamic loading, a routine is not loaded until it's called. All routines are kept on disk in a relocatable load format. The main program is loaded into memory and is executed. When a routine needs to call another routine, the calling routine first checks to see whether the other routine has even been loaded. If it has not, the relocatable linking loader is called to load the desired routine into memory and update the program's address tables to reflect this. And then control is passed to the newly loaded routine. The advantage of dynamic loading is that a routine is loaded only when it's needed. This method is particularly useful when large amounts of code are needed to handle in frequently occurring cases such as error routines. In such a situation, although the program size may be large, the portion that is used, and hence loaded, may be really small. Dynamic loading does not require special support from the operating system. It is the responsibility of the user to design their programs to take advantage of such a method. Operating systems may help the programmer, however, by providing library routines to implement dynamic loading. Dynamic linked libraries, or DLLs, are system libraries that are linked to user programs when the programs are run. Some operating systems support only static linking, in which system libraries are treated like any other object module and are combined by the loader into the binary program image. Dynamic linking, in contrast, is similar to dynamic loading. Here, though, linking rather than loading is postponed until execution time. This feature is usually used with system libraries, such as the standard C language library. Without this facility, each program on a system must include a copy of its language library. This requirement not only increases the size of an executable image, but it also may waste main memory. A second advantage of DLLs is that these libraries can be shared among multiple processes so that only one instance of the DLL is in main memory. For this reason, DLLs are also known as shared libraries and are used extensively in Windows and Linux systems. Dynamically linked libraries can be extended to library updates, such as bug fixes. In addition, a library may be replaced by a new version, and all programs that reference that library will automatically use the new version. Without dynamic linking, all such programs would need to be relinked again to access the new library. The main memory must accommodate both the operating system and various user processes. We therefore need to allocate main memory in the most efficient way possible. One possible method of doing this is called contiguous memory allocation. The memory is usually divided into two partitions, one for the operating system and one for the user processes. We can place the operating system in either low memory addresses or high memory addresses. This decision depends on many factors, such as the location of the interrupt vector. However, many operating systems that include Linux and Windows place the operating system in high memory, and therefore, we discuss only that situation. We usually want several user processes to reside in memory at the same time. We therefore need to consider how to allocate available memory to the processes that are waiting to be brought in memory. In contiguous memory allocation, each process is contained in a single section of memory that is contiguous to the section containing the next process. Before discussing this memory allocation scheme further, we have to address the issue of memory protection. We can prevent a process from accessing memory that it does not own by combining two ideas previously discussed. If we have a system with a relocation register together with the limit register, we can accomplish our goal. The relocation register contains the value of the smallest physical address. The limit register contains the range of logical addresses. Each logical address must fall within the range specified by the limit register. The MMU maps the logical addresses dynamically by adding the value in the relocation register, as we can see right here. The relocation register scheme provides an effective way to allow operating system sizes to change dynamically. This flexibility is desirable in many situations. For example, the operating system contains code and buffer space for each device drivers. If a device driver is not currently in use, it makes little sense to keep it in memory. Instead, it can be loaded into memory only when it's needed. Now we are ready to turn to memory allocation. One of the simplest methods of allocating memory is to assign a process to a variably sized partitions in memory, where each partition may contain exactly one process. In this variable partition scheme, the operating system keeps a table indicating which parts of memory are available and which are occupied. Initially, all memory is available for user processes and is considered one large block of available memory. This is sometimes referred to as a whole. Now eventually, we'll see that memory contains a set of holes of various sizes. Now the figure below depicts this scheme. Initially, the memory is fully utilized, containing processes 5, 8, and 2. After process 8 leaves, there is one contiguous hole. Later on, process 9 arrives and is allocated memory. Then process 5 departs, resulting in 2 non-contiguous holes. As each process enters the system, the operating system takes into account the memory requirements of each process and the amount of available memory space in determining which process are allocated memory. When a process terminates, it releases its memory, which the operating system may then provide to another process. What happens when there isn't sufficient memory to satisfy the demands of an arriving process? One option is to simply reject the process and provide an appropriate error message. Alternatively, we can place such a process into a wait queue. When memory is later released, the operating system checks the wait queue to determine if it will satisfy the memory demands of a waiting process. In general, as mentioned, the memory blocks available comprise of a set of holes of various sizes scattered throughout memory. When a process arrives and needs memory, the system searches the set for a hole that is large enough for this process. If the hole is too large, it is then split into 2 parts. One part is allocated to the arriving process, and the other is returned to the set of holes. When a process terminates, it releases its block of memory, which is then placed into the set of holes. If a new hole is adjacent to the other ones, these adjacent holes are then arranged to form one larger hole. This procedure is a particular instance of a general dynamic storage allocation problem, which concerns how to satisfy the request of a size n from a list of free holes. There are many solutions to this problem. The first fit, best fit, and worst fit strategies are the ones most commonly used to select a free hole from the available set. Looking into each one of these, first fit, we allocate the first hole that is big enough. Searching can either start at the beginning of the set of holes or at the location where the previous first fit search ended. We can stop searching as soon as we find a free hole that is large enough. Best fit. Allocate the smallest hole that is big enough. We must search the entire list unless the list is ordered by size. This strategy produces the smallest leftover hole. And finally, worst fit. Allocate the largest hole. Again, we must search the entire list unless it's sorted by size. This strategy produces the largest leftover hole, which may be more useful than the smaller leftover hole from the best fit approach. Simulations have shown that both first fit and best fit are better than worst fit in terms of decreasing time and storage utilization. Neither first fit nor best fit is clearly better than the other in terms of storage utilization, but first fit is generally faster. Both first fit and best fit strategies for memory allocation suffer from what's called external fragmentation. As processes are loaded and removed from memory, the free memory space is broken into little tiny pieces. External fragmentation exists when there is enough total memory space to satisfy a request, but the available memory space are not contiguous. Storage is then fragmented into a large number of smaller holes. This fragmentation problem can be severe. In the worst case, we can have a block of free or wasted memory between every 2 processes. If all of these small pieces of memory were in one big block instead, we might be able to run several more processes. Depending on the total amount of memory storage and the average process size, external fragmentation may be a minor or a major problem. Statistical analysis for first fit, for instance, reveals that even with some optimization, Given n allocation blocks, another 1/2 n blocks will be lost due to fragmentation. This 1/3 of memory may be unusable. This property is known as the 50% rule. Memory fragmentation can be internal as well. Consider multiple partition allocation scheme with a whole that is 18,464 bytes. Now, suppose that the next process requests 18,462 bytes. If we were to allocate exactly the requested block, then we're left over with a whole of size 2 bytes. The overhead to keep track of this whole will be substantially larger than the whole itself. The general approach to avoid this problem is to break the physical memory into fixed size blocks and allocate the memory in unit-based block size. With this approach, the memory allocated to the process may be slightly larger than what is requested. The difference between these two numbers is the internal fragmentation, or the unused memory that is internal to that partition. Now, going back to external fragmentation, one solution for this may be compaction. The goal of this strategy is to shuffle the memory contents so as to place all free memory together in one large block. Compaction is not always possible, however. If reallocation is static and is done at assembly or load time, compaction cannot be done. It is possible only if relocation is dynamic and is done at execution time. If addresses are relocated dynamically, relocation requires only moving the program and the data and then changing the base register to reflect the new base address. When compaction is possible, we must determine its cost. The simplest compaction algorithm is to move all processes toward one end of the memory. Thus, all holes move into the other direction, producing one large hole of available memory. However, this scheme can be very expensive. Memory management discussed so far has required the physical address space of a process to be contiguous. We now introduce paging, a memory management scheme that permits a process's physical address space to be non-contiguous. Paging avoids external fragmentation and the associated need for compaction, which are two problems that plague contiguous memory allocation. Because it offers numerous advantages, paging in its various forms is used in most operating systems, from those for large servers to those for mobile devices. Paging is implemented through cooperation between the operating system and the computing hardware. The basic method for implementing paging involves breaking physical memory into fixed size blocks called frames, and breaking logical memory into blocks of the same size called pages. Frames are physical, pages are logical. When a process is executed, its pages are loaded into any available memory frames from their source. The backing store is divided into fixed blocks that are the same size as the memory frames or clusters of multiple frames. This rather simple idea has great functionality and wide ramifications. For example, the logical address space is now totally separate from the physical address space, so a process can have a logical 64-bit address space even though the system has less than 2 to the power of 64 bytes in its physical memory. Every address generated by the CPU is divided into two parts, a page number and a page offset. The page number is used as an index into a per-process page table. This can be illustrated right here. The page table contains the base address of each frame in physical memory, and the offset is the location in the frame that is being referenced. As you can see, the logical memory address contains the two parts, the page number and the offset, or you can consider this as a displacement. This references this value which gets the frame. From there, we use that offset in order to displace or figure out where we are within that frame. Thus, the base address of a frame is combined with the page offset to define the physical memory address. We can see this illustrated right here, where the logic memory of an application is then broken apart into the physical memory that is referenced by the page table. Paging is a great strategy. However, we still may have some internal fragmentation. Notice that the frames are allocated as units. If the memory requirements of a process do not happen to coincide with the page bounds, then the last frame allocated may not be completely full. As an example, if the page were 2048 bytes, a process of 72,766 bytes will need 35 pages plus an additional 1,086 bytes. It will allocate 36 frames, resulting in internal fragmentation of 2048 minus 1086, which results in 962 bytes that are wasted. In the worst case, a process would need n pages plus a byte. It would be allocated n plus 1 frames, resulting in an internal fragmentation of almost an entire frame. If a process size is independent of the page size, we expect internal fragmentation to average 1/2 page per process. This consideration suggests that small page sizes are desirable. However, overhead is involved in each page table entry, and this overhead is reduced as the size of the pages increase. Also, disk input and output is more efficient when the amount of data being transferred is larger. Generally, page sizes have grown over time as processes, datasets, and main memory have become larger. Today, typically, it's either 4 kilobytes or 8 kilobytes in size, and some systems support even larger page sizes. When a process arrives in the system to be executed, its size expressed in pages is examined. Each page of the process needs 1 frame. Thus, if a process requires n pages, at least n frames must be available in memory. If n frames are available, they allocate to this arriving process. The first page of a process is loaded into one of the allocated frames, and the frame number is put in the page table for this process. The next page is loaded into another frame. Its frame number is put into the page table, and so on, as we can see right here. An important aspect of paging is the clear separation between the programmer's view of memory and the actual physical memory. The programmer's view of memory as one single space containing only this one program. But in fact, the user program is scattered throughout physical memory. Since the operating system is managing physical memory, it must be aware of the allocation details of physical memory. Which frames are allocated, which frames are available, and how many total frames there are, and so on. This information is generally kept in a single system-wide data structure called the frame table. The frame table has one entry for each physical page frame, indicating whether the latter is free or allocated, and if it is allocated to which page of which process or processes. As page tables are per process data structures, a pointer to the page table is stored with the other register values, just like an instruction pointer, in the process control block of each process. When the CPU scheduler selects a process for execution, it must reload the user registers and the appropriate hardware page table values from the stored user page table. The hardware implementation of a page table can be done in several different ways. In the simplest case, the page table is implemented as a set of dedicated high-speed hardware registers, which makes the page address translation very efficient. However, this approach increases context switch time, as each one of these registers must be exchanged during the context switch. The use of registers for page tables is satisfactory if the page table is reasonably small. Most contemporary CPUs, however, support much larger page tables. For these machines, the use of a fast register to implement the page table is just not feasible. Rather, the page table is kept in main memory, and a page table base register, PTBR, points to the page table. Changing page tables require changing only this one register, substantially reducing the time involved in context switching. Now, although storing the page table in main memory can yield faster context switches, it may also result in slower memory access. Suppose we wanted to access location I. We must first index into the page table using the value in the PTBR offset by the page number for I. This task requires one memory access. It provides us with the frame number, which is combined with the page offset to produce the actual address. We can then address the desired place in memory. With this scheme, two memory accesses are needed to access data, one for the page table entry and the other for the actual data. Thus, memory access is slowed by a factor of 2, a delay that is considered intolerable under most circumstances. The standard solution to this problem is to use a very special, small, fast lookup hardware cache called the Translation Look-Aside Buffer, the TLB. The TLB is associative high-speed memory. Each entry in the TLB consists of two parts, a key and a value. When the associated memory is presented with an item, the item is compared with all the keys simultaneously. If the item is found, the corresponding value field is then returned. The search is fast. A TLB lookup in a modern hardware is part of the instruction pipeline, essentially adding no performance penalty. To be able to execute the search within the pipeline step, however, the TLB must be kept small. It is typically between 32 and 1024 entries in size. The TLB is used with page tables in the following way. The TLB contains only a few of the page table entries. When a logical address is generated by the CPU, the MMU first checks if the page table is present in the TLB. If the page number is found, its frame number is immediately available and is used to access memory. As just mentioned, these steps are executed as a part of an instruction pipeline within the CPU, which adds no performance penalty compared with a system that does not implement paging. If the page number is not in the TLB, this is known as a TLB miss. The address translation proceeds following the steps illustrated here, where memory reference to the page table must be made. When a frame number is obtained, we can then use that to access the memory. If the TLB is already full of entries, an existing entry must be selected for replacement. Replacement policies range from least recently used through round robin to random. Some CPUs allow the operating system to participate in the LRU entry replacement, while others handle the matter themselves. Furthermore, some TLBs allow certain types of entry to be wired down, meaning they cannot be removed from the TLB. Typically, TLB entries for key kernel code are wired down. Some TLBs stored what's called an Address Space Identifier, ASID. In each TLB entry, an ASID uniquely identifies each process and is used to provide address space protection for this process. When the TLB attempts to resolve a virtual page number, it ensures that the ASID for the currently running process matches the ASID associated with its virtual page. If they do not match, the attempt is treated as a TLB miss. The percentage of times that a page number of interest is found in the TLB is called the hit ratio. An 80% hit ratio, for example, means that we find the desired page in the TLB 80% of the time. If it takes 10 nanoseconds to access memory, then a mapped memory access takes 10 nanoseconds when the page number is in the TLB. If we fail to find the page number in the TLB, then we must first access memory for the page table and the frame number, and then access the desired byte in memory. This adds up, so now we need to be able to calculate effective memory access time, which we weight the case by its probability that we can see here. This is denoted as the effective access time. Now, in this example, we have suffered from a 20% slowdown in average memory access. Now, if we were to change this for a 99% hit ratio, which is much more realistic, then we have the following case. The increased hit rate produces 1% slowdown in access time. Memory protection in a paged environment is accomplished by protection bits associated with each frame. Normally, these bits are kept in the page table. One bit can define a page table to be read, write, or read-only. Every reference to memory goes through the page table to find the connected frame. At the same time that the physical address is being computed, the protection bits can be checked to verify that no writes are being made to a read-only page. An attempt to write to a read-only page causes a hardware trap to the operating system. We can easily expand this approach to provide finer levels of protection. We can create hardware to provide read-only, read-write, or execute-only protections. Or, by providing separate protection bits for each kind of access, we can allow any combinations of these accesses. Illegal attempts will be trapped to the operating system. One additional bit is generally attached to each entry in the page table. This is called a valid-invalid bit. When this bit is set to valid, the associated page in the process's logical address space and is thus legal or a valid page. When the bit is set to invalid, the page is not in the process's logical address space. Illegal addresses are trapped by use of the valid-invalid bit. The operating system sets this bit for each page to allow or disallow access to the page. We have the following situation we see here. Addresses in pages 0, 1, 2, 3, 4, and 5 are mapped normally through the page table. Any attempt to generate an address in pages 6 and 7, however, will find the valid-invalid bit is set to invalid, and the computer will trap the operating system. Rarely does a process use all of its address range. In fact, many processes only use a small fraction of the address space available to them. It would be wasteful in these cases to create a page table with entries for every page in the address range. Most of this table will be unused, but would take up a valuable memory space. Some systems provide hardware in the form of a page table length register, or PTLR. This indicates the size of the page table. This value is checked against every logical address to verify that the address is in the valid range for the process. Failure of this test causes an error trap to the operating system. An advantage of paging is the possibility of sharing common code, a consideration that is particularly important in an environment with multiple processes. If the code is reentrant code, it can be shared, as we can see right here. Here we see 3 processes sharing pages for the standard C library, libc. Reentrant code is not self-modifying code. It never changes during execution. Thus, 2 or more processes can execute the same code at the same time. In addition to runtime libraries such as libc, other heavily used programs can also be shared: compilers, Windows systems, databases, and so on. Most modern computer systems support a large logical address space. In such an environment, the page table itself becomes excessively large. For example, consider a system with a 32-bit logical address space. if the page size in such a system is 4 kilobytes, in other words 2 to the power of 12, then a page table may consist of over 1 million entries. Assuming that each entry consists of 4 bytes, each process may need up to 4 megabytes of physical address space for the page table alone. Clearly, we would not want to allocate the page table contiguously in main memory. One simple solution to this problem is to divide the page table into smaller pieces. We can accomplish this division in several different ways. One way is to use two-level paging algorithms, in which the page table itself is also paged, which we can see here. For example, once again, consider the system with a 32-bit logic address space and a page size of 4 kilobytes. A logical address is then divided into page numbers, consist of 20 bits, and a page offset consisting of 12 bits. Because we page the page table, the page number is further divided into a 10-bit page. Because we page the page table, the page number is further divided into 10-bit page number and a 10-bit page offset. Thus, the address space sort of looks like what we have here. We can see here that a logical address is as follows. We have a P1, which is an index into the outer page, and a P2 is the displacement within a page of an inner page table. The address translation method for this architecture can be seen here. Because this address translation works from the outer page table inward, this scheme is also known as forward-mapped page tables. Now, for a system with a 64-bit logical address space, a two-level paging scheme is no longer appropriate. To illustrate this point, let's suppose that the page size in such a system is 4 kilobytes. In this case, the page table consists of up to 2 to the power of 52 entries. If we use two-level paging scheme, then the inner page table can be conveniently be set to 1 page long or contain 2 to the power of 10 4-byte entries. Now, the outer page table consists of 2 to the power of 42 entries or 2 to the power of 44 bytes. This obvious way to avoid such a large table is divided into the outer and into the smaller pieces. We can further divide the outer page in various ways. For example, we can page the outer page table giving a 3-level paging scheme as we can see here. Suppose that the outer page table is made up of the standard size page, 2 to the power of 10 entries or 2 to the power of 12 bytes. In this case, a 64-bit address space is still daunting. One approach for handling address spaces larger than 32 bits is to use a hash page table. The hash value being the virtual page number. Each entry in the hash table contains a linked list of elements that hash to the same location. Each element consists of 3 fields, the first one being the virtual page number, the second one the value of the mapped page frame, and the third a pointer to the next element in the linked list. The algorithm for this works as follows. The virtual page number in the virtual address is hashed into the hash table. The virtual page number is compared with field 1 in the first element in the linked list. If there is a match, the corresponding page table, field 2, is used to form the desired physical address. If there is no match, subsequent entries in the linked list are searched for the matching virtual page number. We can see this scheme illustrated right here. The variation of this scheme that is useful for 64-bit address spaces has been proposed. This variation uses clustered page tables, which are similar to hash page tables except that each entry in the hash table refers to several pages, like 16 at a time, rather than a single page. Therefore, a single page table entry can store the mappings for multiple physical page frames. Clustered page tables are particularly useful for sparse address spaces, where memory references are non-contiguous and scattered throughout the address space. Now usually, each process has an associated page table. The page table has one entry for each process that the process is using. This page table representation is a natural one since processes reference pages throughout the page's virtual addresses. The operating system must then translate the reference into the physical address. Since the table is sorted by virtual addresses, the operating system is able to calculate when in the table the associated physical address entry is located and to use the value directly. One of the drawbacks of this method is that each page table may consist of millions of entries. These tables may consume large amounts of physical memory just to keep track of how other physical memory is being used. To solve this problem, we can use what's called an inverted page table. An inverted page table has one entry for each real page or frame of memory. Each entry consists of the virtual address of the page stored in the real memory location, with information about the process that owns the page. Thus, only one page table is in the system, and it only has one entry for each page of physical memory. We can see in this figure it shows the operation of an inverted page table. Inverted page tables often require that an address space identifier be stored in each entry of the page table. As we can see that the process logical address is composed of the process ID, the PID, the page number, and the offset. Each inverted page table entry is that pair, where the process ID assumes the role of the address space identifier. When a memory reference occurs, part of the virtual address consisting of the PID and the page number is presented to the memory subsystem. The inverted page table is then searched for a match. If that match is found, say at entry I, then the physical address becomes I at that offset is generated. If no match is found, then an illegal address access has been attempted. Process instructions and the data they operate on must be in memory in order to be executed. However, a process or a portion of a process can be swapped temporarily out of memory back into backing store. Then it can be brought back into memory for continued execution. We can see that concept illustrated here. Swapping makes it possible for the total physical address space for all processes to exceed the real physical memory of a system. Thus, this increases the degree of multiprogramming in a system. Standard swapping involves moving entire processes between main memory and their backing store. The backing store is commonly fast secondary storage. It must be large enough to accommodate whatever parts of the process need to be stored and retrieved, and it must provide direct access to memory images. When a process or part is swapped to the backing store, the data structures associated with the process must be written to the backing store. For multi-threaded processes, all per-thread data structures must be swapped as well. The operating system must also maintain metadata for processes that have been swapped out, so they can restore when they are swapped back into memory. The advantage of standard swapping is that it allows physical memory to be oversubscribed so that the system can accommodate more processes than there is actual physical memory to store them. Idle or mostly idle processes are good candidates for swapping. Any memory that's been allocated to these inactive processes can then be dedicated to an active process. If an inactive process that has been swapped out becomes active again, it then must be swapped back in. Most systems, including Linux and Windows, now use a variation of swapping in which pages of a process, rather than the entire process, can be swapped. This strategy still allows physical memory to be oversubscribed, but does not incur the cost of swapping the entire process, as presumably the only small number of pages that it will be involved in swapping. In fact, the term swapping now generally refers to the standard swapping and paging refers to the swapping with paging. A page out operation moves a page from memory to the backing store. The reverse process is called page in. Swapping with paging is illustrated here, where a subset of pages for the process A and B are being paged out and paged in respectively. We'll see this more in a future lecture. In this chapter, we have started our discussion on memory. While we have focused on processes in previous lecture, memory is also an extremely important part to most systems that require some operating system consideration. We've looked at ways that we could allocate memory to processes so that we can then run them. And in the next lectures, we're going to explore this idea more. With all that being said, I'll see you next time.